Okay, moving on to water and its features that support and enable life to occur. If we didn't have water on our planet, we wouldn't be able to be alive, and that's why one of the first things that scientists look for when they look for proof of life on planets out there is they're trying to find water, because that's the only way we would be able to survive on that planet. Maybe at some point we'll find that these alien life forms don't need water, but we haven't found any yet. So these hydrogen bonds that we were talking about are the things that make water cohesive. So I would really strongly recommend that you remember these words when we're talking about water. This word, cohesive, this means that water has a high surface tension because these hydrogen bonds right here are pretty strongly attracted to one another. So they make it so that water has a very high surface tension. If you've ever seen those little insects that seem like they can walk on water, and they put their feet down in the water and they have the little bubble, it seems, right around the bottom? That is because water has a very high surface tension. These V-shaped water molecules are held together by hydrogen bonds, and the bonds are just strong enough to give water a very high surface tension. So this is why things float on top of the water, like this insect that we have right here. Water's high surface tension is, we can put pressure against the water, and the water is going to push back up, and that's why things are looking like they can float on water. If you've ever seen those lizards that are called the Jesus lizards, they run so fast over the water, and you can see how they got their name because they can walk on water. So it gives the top of the water this net-like property that we see. So these unusual properties that make water critical to life, they have to function in all these ways or life wouldn't be possible. They have cohesion, they have a large heat capacity, which we'll look at coming up here, low density as a solid, so that's our ice, and they are good solvents, so things can dissolve in them. And if I were going to suggest that you write anything down today, I would really suggest that you get these four down, these four properties that make water capable of sustaining life here on Earth. They have cohesion, large heat capacity, low density as a solid, and they are good solvents. Got it? No. Oh. All right. I'll post them. You'll be able to find them again. So cohesion is another reason that things like trees can pull water up from the ground all the way up the very, very long trunk up to the leaves at the top. So we've got cohesion, meaning that the water is sticking together. So it's got a cohesive property. So these trees are able to pull the water molecule into their root system, which goes very deep down into the ground. So they pull that water up, and then since the water is attracted to, the water molecules are attracted to one another, that makes them sticky. So they're basically going to be pulled up the trunk of the tree. And then as the water molecule gets up into the leaves, the sun is going to cause it to evaporate. And each water molecule, as it evaporates, is going to go up into the atmosphere, and more are going to be pulled up in order to follow behind it. So if water was not cohesive, then anything that didn't specifically drink water would not be able to be alive, and that would nix most of our plants, which would be very bad for us. And so the next property of water is its high heat capacity. So if you think about out in the nice tropical regions where the weather out there, the temperatures don't swing too much, it mostly stays about stable. Part of that is because water is going to be able to retain that heat inside it. So heat energy that's coming from the sun is going to heat up the hydrogen bonds that are between the two water molecules, and new hydrogen bonds are going to form as they start to move around pretty rapidly against one another. So you see disruption and then a new bond, and then disruption and then a new bond. And so because heat energy from the sun is used up in breaking and reforming these bonds, water temperature doesn't increase by much. So the ocean water is going to be pretty stable. And then molecules that make up sand, on the other hand, don't have so many hydrogen bonds, so the heat of the sun just increases the temperature. If you've ever been out to the beach and you're running on the beach, the sand feels pretty cold in the morning, but as you get into the afternoons where the sun has been beating down on the sand gets really hot. But if you were to put your feet in the water at any point in time, the water temperature remains pretty much stable. And that's because of the water's high heat capacity. So 60% of your body is water, and this is what helps you to maintain a relatively constant body temperature. So your homeostasis, this equilibrium that you see inside of your body, this stable temperature, 98.6 degrees, is maintained because 60% of your body is made up of water. Water also has low density as a solid. That means that if you put ice cubes into your drink and then you pour the drink on top of them, the ice cubes are going to float up from the bottom. And that's because the frozen water has a lower density than the liquid water. So these molecules are going to be in a crystalline structure, kind of the same reason we get snowflakes. And it's going to form them in this lattice, and they're going to stay in kind of a stable frozen state. But in liquid water, these hydrogen molecules are moving past one another pretty quickly. They're allowed to move about freely, and so liquid water is going to be underneath the frozen water, which is on the top. This is important for life. Think about what would happen if you were to have lakes or ponds freeze from the bottom instead of freezing from the top. When they freeze on the top, this layer of ice stays across the top of them, and the living things, the organisms, the fish, the insects, the turtles, they're all underneath the water under this layer of ice on the top. If it went the other direction and it froze from the bottom, they would all freeze too, and that would be a bad thing for life. So here you can see relative area occupied by the same number of H2O molecules. So notice this is about a fourth bigger than the liquid water is. But there's other molecules out there where that doesn't happen, where when something freezes or comes together as a solid, it goes thunk down to the bottom. Here we see that water is a good solvent. If you think about pouring salt into water, like if you're boiling some spaghetti, you put your salt into the water and it dissolves as Na+, sodium is plus, and chlorine or chloride minus ions. And so when placed in water, something that's an ionic compound, they break apart, and the positively charged sodium ions go one direction, the negatively charged chlorine molecules are going the other direction, and they get surrounded by the water, so that's why they stay dissolved in this solution.